In this video, we work our second example problem for Rolle's theorem. The problem statement says determine whether Rolle's theorem applies to the given function on the given interval. If the theorem applies, find the x values that are guaranteed to exist by the theorem. We're given this function on this interval. Now, remember what the theorem says. It says if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, and f of a and f of b are the same, then there exists at least one x value on the closed interval from a to b such that f prime at that x value is equal to 0. So basically what it's saying is that we're guaranteed to have a relative extrema corresponding to a nice smooth location on that curve on the interior of the interval from a to b. And actually, since it is the interior, I think I should probably change these brackets. It should probably be like this. So there's at least one x value on that open interval from a to b such that f prime at that x value is equal to 0. Okay, so we need to check to make sure our function is continuous and differentiable, and the function values are the same at the left endpoint and the right endpoint. So we've got this function. It's a polynomial. We know polynomials are continuous and differentiable everywhere, so they're going to be nice and smooth. So the first two requirements are satisfied. We'll just write, since f is a polynomial, f is continuous and differentiable on the entire real line. So f is continuous and differentiable on the closed interval from a to b. So those first two requirements are satisfied, continuous and differentiable. Now we need to check the function value at x equals 1 and at x equals 3. So we'll evaluate f at 1, we'll evaluate f at 3. We're just going to replace x with 1 and 3 and then simplify. When I substitute x equals 1, I get 1 minus 7 plus 9. So that's 1 plus 9 is 10, minus 7 is 3. And then if I evaluate f at 3, I don't know if I'm going to get the right answer here. I get 27 minus 21 plus 9. So what's that, 36 minus 21, or 15? Okay, so the y values are not the same. So f of 1 and f of 3 are not equal to each other. So our theorem does not apply. Now, if we were given the same function on a different interval, instead of the interval from 1 to 3, an interval from one value to another value where the y values happen to be the same, then we would be guaranteed some x values where the derivative is 0, or at least one x value where the derivative is 0 on the interior of that interval. But since our function is equal to 3 at one value and 15 at the other value, we're really not sure what happens in between. So, what does this tell us? Everything that we've done so far actually tells us that our graph roughly looks like this. When x equals 1, y equals 3. I'm just going to use 5, 10, 15 here. And when x equals 3, y equals 15. Now I know my function is smooth. It's a polynomial, so it's continuous and it's differentiable. But the problem is, since my function values are not the same at x equals 1 and x equals 3, the function might just be increasing on the interval from 1 to 3. It might just look like this. And so we aren't guaranteed any x values on the interval from 1 to 3 that give us a derivative of 0. But it's also possible that the function looks like this, and we have a derivative equal to 0 there. Or maybe it looks like this, and we have a derivative equal to 0. So we don't really know, because the y values are different on the left and the right-hand side. We might have a relative max or a relative min on the interval, or we might not. The function might just be increasing from one point to the other. The theorem does not apply, and we aren't guaranteed any x values on that interval that correspond to a zero derivative. But we might have some, or we might not. Now let's modify this problem a little bit. Let's call this example 2 star. Let's say we have the same function, but instead of the interval from 1 to 3, maybe we're interested in the interval from -3 to 1. Well, we know f is a polynomial, so it's continuous and differentiable on any interval we choose. So that part is still satisfied. We just need to evaluate the function at -3 and 1. Now we know that when we evaluate it at 1, we get 3. We've already done that. Let's see what happens when we evaluate at -3. Then I've got -27 plus 21 plus 9. So that's negative 21 plus 9 is 30. 30 minus 27 is 3. And they're the same. So we know that f is a polynomial. So it's continuous and differentiable, and the function values are the same. So we are guaranteed a point where the derivative is equal to 0. So we'll say since f is a polynomial, it is continuous and differentiable on any interval, but particularly on this interval. Since f is a polynomial, continuous and differentiable on this interval, let's say since f f1 is also equal to f of -3, the theorem applies, Rolle's theorem applies. So I don't know what my graph looks like, but I know that it passes through this point, and it passes through this point, and x equals -3 also has a function value of 3. So I know we start here and we end here for this particular version of the problem. It's a polynomial, and I start at I start with a y value of 3, and I end with a y value of 3. Since that's true, either the polynomial is just a constant, and we can tell from the equation that it's not. It might have a derivative of 0 everywhere, but since it's got this x cubed in the x term here, then we know that that's not true. But we know that something interesting has to happen between -3 and 1. Since it's nice and smooth, we have to go up at some point. Or if we happen to go up at some point, we have to come down. And we're going to come down in a very smooth way because the function is differentiable. So we'll have a relative max at that location if that's what happens. Now, if our function starts at x equals -3, y equals 3, and then goes down first, then it has to come back up. And when it comes back up, since it's doing so in a nice smooth way, we're going to have a derivative equal to 0 at that relative minimum value. Now you might have a lot of interesting things happening. You might have a graph that just goes up and down and up and down, and then you might have multiple x values that correspond to a derivative of 0 on that interval. So we don't really know, but we do know that there is at least one x value on the interval from -3 to 1 where the derivative is 0. So the question says, determine whether the theorem applies. It does. If the theorem applies, find the x values that are guaranteed to exist by the theorem. So we need to find f prime. And then once we compute f prime, we'll set it equal to 0 and solve for x, and we'll only be interested in those x values on the interval from -3 to 1. So f prime is the derivative with respect to x of f. And the derivative of x cubed is 3x squared by the power rule. Bring the power down, multiply by x to the 1 less power. The derivative of a constant times x is just the constant, and the derivative of a constant is 0. So f prime of x is equal to this. Now we're going to set that equal to 0 and solve for x. So that means that 3x squared is equal to 7. So that means x is equal to, or x squared is equal to 7/3. And you take the square root of both sides. Don't forget the plus or minus on the right. So x is equal to plus or minus the square root of 7 divided by 3. 7 divided by 3, what's that? That's what? 2.33. So we're taking the square root of 2.33. So that's plus or minus a number that is between 1 and 2. And it's closer to 1 than it is to 2, I think. So we're saying plus or minus 1 point something. So I think that the positive one is going to be outside our interval, and the negative one is going to be inside our interval. So we'll say since x equals the negative square root of 7/3 is in the interval from -3 to 1, it is the x value that we're looking for. I don't actually know what that number is, but we could use a calculator and find out what it is. It's going to be plus or minus some value. And we can look at the calculator on desmos.com to see what that is approximately. And so using my calculator, I found that my x value is approximately 1.528, plus or minus 1.528, since the negative version of that is on the interval from -3 to 1. That's the one that we're looking for. Now, if our interval included, or this positive x equals 1.528, that would be a solution as well. So let's say we have the exact same function, but instead of the interval from -3 to 1, we have the interval from -3 to 2. Well, provided that the function value at 2 is equal to the function value at -3, then we would get both of those x values. So we know that the function is continuous and differentiable because it's a polynomial. So let's evaluate the function at 2. So we've got 8 minus 14 plus 9. 8 and 9 is 17. 17 minus 14 is 3. That's cool. Great. F of 2 is equal to 3. And we know from previous calculations that f of -3 was equal to 3. So we'll say since f is continuous and differentiable, and f of 2 is equal to f of -3, then Rolle's theorem applies on the interval. And in that case, the two x values, or the x values that satisfy the requirements of the theorem, are both of these, x equals plus and minus the square root of 7/3. Okay, so we've done all of those calculations, and what does that tell us about our graph? Well, it tells us this. Our graph looks roughly like this. What do we know? We know that when x equals -3, the y value is 3. And this is not to scale, so I'm going to say that's 5, 10, 15. And we said at x equals 1, the y value is also 3. And we said at x equals 2, the y value is 3. Those are all supposed to be on the same line. It's a little bit difficult to see. And then we know that at x equals 3, the y value happened to be 15. And so on the interval from 1 to 3, the theorem did not apply because the y values were different. But on the interval from -3 to 1 and the interval from -3 to 2, the y values were the same. So we were guaranteed to have a relative min or a relative max on each of those intervals. Or not just a relative min or a relative max. We're guaranteed to have an x value that gives us a 0 derivative on each of those intervals. And because we're starting and ending at the same place, those are going to correspond to relative minima or maxima. Now we said at x equals plus or minus the square root of 7/3, our derivative is 0. Let's find the corresponding y values so that we can graph those points. F evaluated at plus or minus square root of 7/3. A little bit tedious, isn't it? So we're going to have plus or minus 7/3 times the square root of 7/3. Then we have minus plus 7 times the square root of 7/3 plus 9. And we need a common denominator here, so we'll multiply by 3 over 3. And here we'll multiply by, well, I'll just leave the 9 alone. So I'm going to have plus or minus, or this is going to be minus or plus 21 over 3. And then I've got plus or minus the 7 over 3. So that's kind of looks really bad. I think I'll just use the Desmos calculator to figure out what those values are. Never mind. Because of the plus or minus, I'm making a big mess. But basically, we just want to find the y values there. Okay, so here are the same 3 examples, but on Desmos.com. So we've got our function f of x equals x cubed minus 7x plus 9. And for the first part, we were asked about Rolle's theorem on the interval from 1 to 3. The question is, does Rolle's theorem apply to the given function on the given interval? If so, find the x values that are guaranteed to exist by the theorem. Well, on the interval from 1 to 3, if we evaluate the function at 1, we get a y value of 3. And if we evaluate the function at 3, we get a y value of 15. Now, the theorem says that if those two y values are the same, Rolle's theorem does not apply. But notice that we actually do have an x value that corresponds to a 0 derivative. It looks like it's somewhere between 1 and 2. It's approximately right there. But the theorem did not allow us to find that. The theorem just said that, or we just know, excuse me, that the theorem doesn't apply. So the function might have a value, an x value on the interval that has a derivative equal to 0, or it might not have a function or an x value, excuse me, where the derivative is equal to 0. But we can see graphically that there's a point. There's a point there where the derivative is equal to 0, but it wasn't guaranteed by the theorem in that case. So we said, okay, well, if we're on this interval from 1 to 3, the theorem doesn't apply. So let's look at a different interval instead. We're looking at the same function. And now we're interested in the interval from -1 to, or -3 to 1. So we're just interested in that part, the purple part of the function. Now at x equals -3, we evaluated the function there. We got a y value of 3. And at x equals 1, we evaluated the function there and we got a y value of 3 as well. Since the y values are the same, we're guaranteed to have some x value on the interval from -3 to 1, where the derivative is 0, and I think we can see that it's right there. The way we find that value is by computing the derivative. We did that on paper. We found that the derivative was 3x squared minus 7, and then we set that equal to 0 and solve for x. We actually get two x values. X equals negative square root of 7/3, and x equals positive square root of 7/3. The negative value is the one on the interval of interest. So, whoops. Square root of 7/3 is actually 1.527 approximately, and we're on the interval from -3 to 1. So the positive one is beyond the interval of interest, but that negative one, negative 1.527, is probably that point right there. So let's plot that point. Oops, it's supposed to be the negative one. There's our local max that's guaranteed to exist, and the x value guaranteed to, or the x value that corresponds to that local max or relative max is this negative square root of 7/3. Now, if you're saying to yourself, is there another way that I could have seen that graphically? Well, you can. We could just graph the derivative function and say, okay, well, when is the derivative equal to 0? Well, it's equal to 0 right there. Looks like it's close to 0 there at negative 1.528. Well, at x equals negative 1.528 approximately, we've got a 0 derivative there. And it looks like at x equals positive 1.528, we've got a 0 derivative as well. When we did the calculations by hand, we found that that value was the square root of 7 plus or minus the square root of 7/3. And when we use Desmos to approximate that, we see that that's actually the exact answer, where these are numerical approximations out to the thousandths place. And if we want to, we can always look at the tangent line there, make sure the tangent line is horizontal, and it is. Now, the theorem says that we were guaranteed at least one x value on that interval. But if our interval had included this x value and this x value, well, then we would have been good to go. We would have found both of them. But again, the theorem has to apply. So we need the function to be continuous on the interval of interest. We need it to be differentiable on the interval of interest. And we also need the function values to be equal at the ends, at a and b, for a particular interval. So we said, okay, let's look at the interval from -3 to 2. And it turned out that when we computed f at 2, we got a y value of 3. So we said, yes, that's good. That's the y value that we're interested in. So let's graph that, evaluate the function at 2. We had already evaluated at -3. So we made our function, we just made our interval a little bit bigger so it would include both of those values. Then both x equals positive square root of 7/3 and negative square root of 7/3 are on the interval of interest. So we get two x values. Now the theorem says there is at least one x value that corresponds to a 0 derivative. If on this interval, it turns out that there are two x values that correspond to a 0 derivative. And we can see those if we graph the derivative function again. Say that 0, the derivative is 0 when that function, the original function, has a slope of 0. The derivative is 0 here when the original function has a slope of 0. Now this 0 of the derivative corresponds to a relative max, and this 0 of the derivative corresponds to a relative min. And of course, each of those corresponds to a horizontal tangent line, so you can always draw the tangent lines and make sure that they're actually horizontal like they're supposed to be. All right, I think that's it. That's it for that example.